This is our fourth lab, and the topic is going to be preparing your plots for publication either in your thesis or for a journal publication. Some of the topics we're going to cover is how to add or modify titles, this concept of overall themes. Then I'll make the distinction between themes on the one hand versus scales and guides on the other, and then finally talk about how you're actually going to go about preparing your plots for publication. So we'll begin with producing this plot called plot 0. And there's plot 0 there, and we're going to have our plotting function. We're going to add to it geom point to make a scatter plot, and we're going to have a whole bunch of aesthetic mapping. We're going to put displacement on the x-axis, city mileage on the y-axis. We're going to map the size of the markers onto city mileage, and then we're going to color the markers by drive and have their shapes vary with a different drive. So that would all produce this plot 0. And our goal is to eventually modify that plot to produce something like this. In order to do that, we're going to need to cover some topics: titles, themes, scales, and guides. So we begin with titles. So we just saw plot 0. And now what I want to do is start off with plot 0, add to it as a layer a bunch of code that will give me plot 1. And here's going to be my plot 1, and it's going to have some plot title. It's going to have a plot title. I'm going to have modified the titles on the y and x axes and modified the titles on the legends. So that's my goal. So how am I going to mess around with these titles? What I'm going to do is I'm going to start off with my plot 0 and then add as a layer the labs function. So there's the labs function. That's the function that's going to be used to manipulate these titles. There is its open parenthesis, and down here is its closed parenthesis. At the end of each of these lines, you see a comma, which means that I could have strung this out into one long line, but I chose to put it on 3 lines because essentially there's 3 different things I want to do. I want to control the overall title, the title of the X and Y axes, and the title of the legend. So, beginning first with the overall title, to stipulate the overall title, I use the keyword title, and I just write in what I want my title to be. Notice the quotation marks. This is my plot. Do you like it? Note this \n. What's that doing? The \n is producing a line break at this point, so this title is spread over 2 lines. Now what I want to do next is manipulate the y and the x-axis titles. So I say x equals, and then specify the title I want on the x-axis, y equals, and then specify the title that's on the y-axis. Note once again, quotation marks, the separation by commas. So that's pretty straightforward. The next part is a little trickier, as my goal is to change the titles on the legends. So to begin with, let's think about this legend here. Where did this legend come from? The reason we have that legend is up here in our original plot. We mapped size onto city mileage. So in order to identify this legend so that we can change its title, we first need to identify it, and we identify it by size equal, because this is a legend that arose from the mapping of size on the city. And once we've identified it with size, we just give it whichever title we want. And similarly for the other legends. So this legend here arose as a consequence of mapping color onto drive. So if we want to modify its title, we say color equal, and in this particular case I've said drive type, and there is its title. And finally, this last legend, arose from the mapping of shape onto drive. So to change its name, I specify shape equals, and indicate what I want to have. You can see that here. Type of drive is going to be the title of that legend. So if you look at this last plot, this plot 1 that we just created, notice that we've got drive type and type of drive, and they're separated. In all likelihood, you would want to have these two legends combined. But think about what happened here. We said the legend that arose as a consequence of the mapping of shape on the drive should have one title, and the legend that arose as a consequence of mapping color onto drive should have a different title. By giving them different titles, we've of course forced them to have separate legends. If we want to combine them into a single legend, which is what we do down here, which is a legend that both combines the shape and the color mapping, we just give them the same title. Shape equals, color equals, and then those two legends are combined. I should note that if you look carefully at the markers in this legend, they're infuriatingly small. Eventually, we shall address that, so don't worry about that now, even though it looks really ugly at this point. Now I want to shift topics and make the distinction between themes on the one hand and scales and guides on the other hand. So themes. Themes are those components that are independent of the data. And guides and scales are components of the plots that may vary with the data or are data dependent. So if we think about themes that are independent of the data, those components that are independent in data, what would they include? Well, they would include features like the location of this title. Right now, it's left justified. I could have it center justified, or I could have it right justified. It's got a particular font and a particular font size. If I look at the background of this plot, I notice that it's gray in color, and I notice that there are these white grid lines. So those are all features of the plot that are independent of the data. They've got nothing to do with the data. On the other hand, there are other features of this plot that are dependent on the data. So if I look at the x-axis, for example, I see the numbers go from 2 to 7. Or if I look at the y-axis, for example, I see the numbers go from 10 to 35. Well, obviously, those values are going to vary from one plot to another because the plots are data dependent. Why is all this stuff important? Why this stuff is important is that the guides and scales are going to differ from one plot in your thesis to another plot in your thesis. On the other hand, you would want the thematic components of your plots to be the same for all of the plots in your thesis. So that's why we make this distinction. So starting with this idea of themes, I want to address this notion of an overall theme. And when we left off, we had plot 1A. That's where we were with plot 1A. And it has a particular overall theme. And in this case, it's the default, which is theme gray, and that gives it its overall appearance. But we can override that default by adding to it, we see that here, a different theme. So we've begun with our plot 1A and created plot 2 by adding to it the code with a plus sign, the code theme black white, and that gives us this. Alternatively, starting with plot 1A, we add theme classic, as is shown here, and that gives us plot 2A. And so we're going to start working around in these next few slides with this plot 2. So there are, however, some additional overall themes that you can use, and you can see in every case they're added with a plus sign. And these particular themes are available if you download the package GG Themes. And here I can added the theme Economist, theme Solarized, theme Tuft, and theme Wall Street Journal. So now I want to go over a theory of themes. And these are my ideas, so I wouldn't take them too seriously, but they're just the way that I've organized this next series of about 10 slides. So the first thing is that all the plots are going to have somewhere between 50 or 60 different components that we're going to think of as being elements. And these elements aren't just a random assortment of things. They exist in clumps, and within those clumps there is a hierarchy. So the features of these elements, those are controlled by element functions. And there's three really important functions for controlling the features of these elements. And they are element text. It's going to control the features of elements which are essentially text. Element line, which will control the features of those elements which are essentially lines. And element rect, which is a function that will control the features of those elements that are essentially rectangular. The third idea is that every plot has its overall theme. And the default is theme black and white, but you could override that, for example, with theme economist. And that provides the default values for those different 50 to 60 theme elements. In preparing your plot for publication, what you're likely to do is to use the element functions to fine-tune your plot to make it more to your desire. The fourth notion is that because these elements are arranged in a hierarchy, you can take advantage of that and save yourself some typing. So you can reduce typing and simplify coding. And then finally, there's this element blank function that you can use to get rid of components that you don't want. So the first idea is that there is a hierarchy of elements, and also linked with it this notion of inheritance. So here we see right here a cluster of elements. There is a cluster. And if you look at what's going on here, you've got axis text X, and you've got the plot title, and you've got axis title Y. These are all text in nature, and they're going to be controlled by the element text function. And there's going to be inheritance in the sense that axis text X will inherit from axis text, and that will inherit from text. And then there's another cluster here, including things such as axis ticks, or the line that makes up the or the y-axis, and they're all inherited from line, and they're going to be controlled by the function element line. And finally, there's a third large and important cluster where the components are essentially rectangular, like the background for the panel, the background for the plot, the background for the legend, and they're going to be controlled by the function element rect. So the second idea is that elements are controlled by these element functions. So what we have here is a reference slide that speaks to the type of features that can be controlled by the element text function if you're dealing with a feature which is essentially text. And I'll go through this fairly quickly. What are some of the features of text that you might want to control? And again, this is a reference slide. We'll get into the specific code later. You might want to control the family, which by default is Helvetica. Maybe you want to make it Arial. The face, by default it's plain. Perhaps you might want to make it bold. Perhaps you might want to make it italic. The color, by default is black. You might want to change that to red. And if you think of that earlier slide that showed you could have things like bisque 2 or goldenrod, you could see a whole wide list of colors. The size you can change, the horizontal or vertical justification. By default, the angle of the text is going to be horizontal, but you can rotate it 90 degrees with code like this. Earlier on, we showed the \n. We wanted to produce a line break, and this will change the line height. And finally, we've got margins, because if you look at some of your plots, you might notice that in some cases the title is squished up a bit closely to the plot itself. You might want to change that. So here we've got a bunch of elements which by their very nature are rectangles. And the main thing to remember when dealing with elements which are essentially rectangles is, if you recall this slide here that we addressed earlier when we went over the scatter plot and said that we had these 25 different shapes. The important point to remember if you're dealing with an element which is essentially a rectangle is it's going to act like one of these guys, in the sense that if there's our rectangle, fill equals is going to determine the predominant color, and color equals is only going to control the border. So here are some of the features, and this just refers to what I said earlier, that the fill and border color are controlled by fill equals and color equals. You can specify size equal and line type equal, but if you specify slide, size, and line type, what that's going to deal with is the size, the thickness, and the line type of the border. So these two things only refer to features of the border of the rectangle. And finally, we've got a bunch of elements which are essentially lines, and they're going to be controlled by the function element line. And here are some of the features of lines that you might want to control: their color, their thickness, their line type, and what they have at the end. So the third idea is that every plot has its default overall theme. And so when we left off, we had plot 2 that had a particular default overall theme, which is theme black and white. And then in preparing your plot for publication, what you're going to do is use the theme function to make alterations so that the plot is more to your desire. So what we just saw back here was our plot 2 that has its overall theme controlled by theme black-white. So what is theme black-white actually doing? So we want to see what theme black-white is actually doing. What we can do is come back here and find our plot. There's R. And in R, I can type in theme black-white, and as I go through this, look at the panel in the lower left-hand corner. When I select theme black and white and hit Control-Shift-Enter, a whole bunch of stuff scrolls through very quickly. So if we come back here, I typed in theme black and white, hit Control-Enter, and what scrolled through so very quickly that we couldn't see it was all this stuff, and that's what I want to examine now. So there's a bunch of stuff that we see in this slide. To begin with, we see a listing of our different elements. So we see a listing of our different elements, and they include things like text, and axis text, and axis text, and this slide only shows a few of them: the legend, position, plot background, etc. And we see some indication of the element functions. So we see element text associated with this guy. We see element line associated with this guy. We see element rect associated with this guy. And we've also got sort of an oddball here. We've got rather an oddball here in the case of legend position, which isn't controlled by an element function, but rather some specification that it's just going to be on the right. So we see a list of the elements, and we see the element functions, and we also, if we look carefully, see evidence of inheritance. Look at the features associated with text. And now look at the features associated with element text. And what you notice is there's a whole bunch of nulls. And the reason that there's a whole bunch of nulls is that these features here are going to be inherited by axis text. So the inheritance from text to axis text is worth noting. But also worth noting is that, for example, although for color it's black for text, for the axis text it's been overridden to be gray 30, which is kind of a light gray, and the size of text overall is 11, but the axis text is going to have this num 0.8, which means that the initial text size of 11 is going to be multiplied by 0.8 to give the size of the axis text. So the whole idea is that the overall theme will determine the overall appearance of our plot, and we're going to use these functions nested inside theme to override those defaults. And we're also, for certain elements, legend position, we're going to have to change those directly. So finally we get our code. So recall, we left off with plot 2 that has a particular appearance because its overall theme was theme black and white. And now we're going to use the information we've seen in these last few slides to modify that plot to make plot 3. So here is the specific code that's going to do that. So we're going to start off with plot 2. We're going to make plot 3, and we're going to do that by adding a layer. And the main thing to note is that the layer that's added is the theme function. So there's the theme function, and there's its open parenthesis here, and its closed parenthesis all the way down here. And so here I've got all this code that's going to override the default. Now note that at the end of each line, there are commas. And as always, I could have strung this out as some wickedly long line, but I decided I didn't want to do that. First of all, it'd be almost impossible to read, and we're going to see a pattern that's going to be recurring in each one of these lines when we use the code to modify the elements. And the basic process is, first we're going to identify the element of interest. So in this case, we're going to start off by identifying plot title. And there's the plot title right there. So we identify the plot title. And then we're going to use our function, the element text function. There's its beginning and its closed parenthesis. And inside that, we're going to make the adjustments we want to make. So we want to specify the color to be red, the size to be 22, and the horizontal justification to be 0.5. And you can see that it's red, and you can see that the justification has gone from being left justified. Now, because of this HJust, it is centered. Let's pick another element. And we're going to see that the process is going to be really quite similar in that we start off by identifying the element we're interested in. Axis text X. Where is the axis text X? Well, that's these numbers down here. So we identify them, we use the element text function, and we specify what we want. Size is 22, we've made them metallic, we've colored them red. Let's pick another element, axis title Y. Where is our axis title Y? There is our axis title Y right there. It's text, so we use the element text function with its open and closed parenthesis. And inside we change the features we want to change. We make the color green and the size 28. So now we're going to do something different. We're going to look at the plot background. And this is the plot background here, the whole background of this plot. So we identify it, we name it. It's a rectangle. So now instead of using the element text function, we use the element rect function. There's its open and closed parenthesis. It's one of these guys that is a rectangle. So fill is the predominant color. Color is only the border. So we say fill equals azure. And if you look at this in color very closely, you can see that this background is azure in color. The specification of color and size is only going to control the border. So we said we want the border to be black and we want it to be of size 3. Axis line X. Axis line X. This line here is the line that makes up the x-axis. So we specify the element. Because it's of a line, we use the element line function. open and close parenthesis. We determine the thickness with size equal and the color with color equals. So everything up until now has used one of these element functions. The big ones being element text, element rect, and element line. And now we're going to deal with rather an oddball. What we're interested in is here's our legend, which by default would have been here, and now we want to move it up to a top position. How do we do that? We do legend position equals, and then we do top. So, the fourth of the 4 or 5 really important slides. How are you actually going to do this when you're making a plot for your thesis or the publications? And these are just some of the steps you can go through to accomplish that. First thing is, what is it you want to do? So let's say, for example, you realize that by default, the legend is off here to the side, and what you want to do is move it up to the top. So you decide what it is you want to do. And as we saw in the previous slide, the overall process is to first identify your element and then operate on it within the theme function. Well, the first thing you've got to do is identify, name the element. Well, how do you figure out what the name of this guy is? Well, the way you figure out the name of this guy is to go into R, and you can type in question mark theme. You type in question mark theme and hit Control Enter. And now what to focus on is the lower right-hand corner. So if you focus on the lower right-hand corner, down here I'm going to see if I can scroll through it. There we go, scrolling through it. And see if I can find legend position, legend box, legend background. Got to be a legend position here somewhere. There it is. I finally found it. There's legend position. There's legend position. So the basic idea is you just type in this question mark theme and use that to get a listing of the different elements, and you can use that as the starting point to make the modifications. So you need to name the thing. In this case, you wanted to determine the name, legend position, so you did the question mark theme. Once you know the name of it, you can use the manual or go online and get other information. And then within this theme, you make the changes that you want to make. The fourth idea is that we can use the fact that these elements exist in a hierarchy, and elements at the lower levels inherit from elements at the upper levels. Take advantage of that to reduce the amount of typing we're going to need to do. So for example, if we look at axis text Y, it inherits from axis text, which inherits from text, and we can take advantage of that fact. So for example, let's say we want to produce a plot like this. And the important feature of the plot like this is that relative to the default, I've increased the font size of all or most of the text. And one way to do that would be just shown here, is that for each one of these elements, plot title or axis text X or axis text Y, for all of these, I specify within theme, it's my open and close parenthesis of theme, I specify the size of the text that I want to have. So that would be one way to do business, but involves an awful lot of typing. An alternative way to do business is that within my theme function, and there's its open and close parenthesis, I simply say that for text, I want the size to be increased, and all these other components will inherit that size increase. They'll inherit that size increase from text, and the size of those components will be increased. However, if you look at this really carefully, you'll see that that's not exactly what's happening. It's not exactly what's happening. These two plots are not exactly identical in the sense, if we look at, for example, axis text X here and compare it with axis text here in this lower set of numbers, the font actually seems to be smaller than in the upper set of numbers. So what's going on here? What's going on here, if we go back to this slide, when we ran theme black and white, to get the list of the elements and their features that are determined by theme black and white, we noted that for element text, its font size was arrived at by inheriting the 11 from text and then multiplying it by 0.8. And that's exactly what's happening here, is that this font size of 24 is inherited, but then it's multiplied by 0.8, and that's why it has a slightly smaller font size. But there's something that's far more important that's happening in this slide. What's far more important that's happening in this slide is that if we look at how we produce this plot, how do we produce this plot? We started off with plot 1A, and that was a very old plot that we produced, and we added to it something called My Theme 1. What's My Theme 1? Well, My Theme 1 was specified up here, and it's an object that consists of theme black and white, added to it all these thematic components. And so that's what produced plot 3A. Where did plot 3B come from? It started off with the same really old plot 1A and added My Theme 2. And what's My Theme 2? My Theme 2 is an object that consists of theme black and white, added to it all these thematic components. And so, if you recall what I said at the very outset, the whole idea of themes is that they refer to those features of the plots that are data independent. And the basic notion was you would want to have all the plots in your thesis had the same overall appearance. So the point is that what you will want to do is create your own version of My Theme 1 or My Theme 2 and then apply it to all the plots in your thesis and publication, and that will give them the same overall general appearance. So the fifth idea is we've got this utility function element blank that we can use to get rid of elements that we don't really want. So I'm going to start off by making this object called A, and there's the code that makes it, and that's what the object A consists of if we were to print A. And then I want to make B, and B is going to be like A, except you notice that A has these little grid lines, those white grid lines. I want to get rid of those white grid lines. So to create B, I start off with A, and as always, I add to it as a layer the theme function. And there's the open and the close parenthesis of theme. I name the element, panel grid, that I want to get rid of, and then I whack it with element blank, so I'm producing this individual that has the grid lines removed. Plot C. I look at plot C, and what I want to do is I want to get rid of these axis titles. I don't want to have those axis titles present in my plot C. So I start off with plot A. I add as a layer theme with its open and close parenthesis. I indicate what I want to get rid of, the axis title, and then I hit it with element blank. And then finally, I want to produce plot D. And in the case of plot D, I want to get rid of the axis text. So the code that I write is to start off with plot A, add as a layer the theme function with its open and close parenthesis, identify the element that I want to get rid of, the axis text, hit it with element blank, and you can see that the axis text has been deleted. So recall that I made a distinction between themes on the one hand and scales and guides on the other. And themes refer to those parts of the plot that are independent of the data, and scales and guides refer to those parts of the plot that are dependent on the data. And so when you put together the plots for your thesis, what you want to do is have a common theme so that all your plots look about the same. Now when we think about scales and guides, for the most part, they're going to work in the background and you're not going to have to deal with them. However, sometimes in preparing your plots for your thesis, you are going to have to deal with scales and guides. I'm not going to go into a great deal of theory on scales and guides. I'm going to give some superficial consideration of how they operate, and then I'm going to move on to some examples. And my hope is that I don't expect you to have a deep understanding of scales and guides, because goodness knows I don't, but hopefully you will have enough of an understanding of scales and guides so that the recipes and examples that I present, if not crystal clear obvious, should at least seem plausible. So I'm going to begin with an overview slide here. So what is a scale? The way I think of a scale is it's the function that brings about an aesthetic mapping. So let's think about if we were to do an aesthetic mapping, such as shown here. We've mapped the X location onto the variable displacement, the Y location onto the variable city, and color onto fuel. And I want to begin with considering first these guys, the mapping of the X and Y location. So the scales are the functions that bring about that mapping. And one way to think about it is that what these scales are going to do, what these functions are going to do, is take the information that's in the data frame and convert them to something that's in the mind of the computer. So if we start off by considering these two mappings here, and here's our data frame with the values of displacement and city mileage, we're going to begin with scale x continuous. So scale x continuous is a function. And it's going to take what's in the data frame, these numbers that go from about 2 to about 4-ish, and it's going to convert them to something on a 0 to 1 scale that the computer can work with. And similarly, we've got this variable city in the data frame, and scale y continuous is the function that's going to take that information and convert it into some sort of number that goes from 0 to 1 that it can put on the y-axis. So that's how it's going to deal with the X and the Y mappings. How about this mapping of color onto fuel? Well, again, the scale is the function that's going to bring about the aesthetic mapping, and the scale that's involved in this case is going to be scale color hue, which is the scale that's used when color is mapped onto a discrete variable such as fuel. So if we think about our data frame, we've got this variable fuel, and it's got these two levels. It's got an R and it's got a P. So what the scale is going to do is it's going to look at the R and it's going to look at the P, and it's going to produce this color wheel. It's going to produce this color wheel, and it's going to take the R and the P, just take the R and put it right there, take the P and put it right there. It's going to locate these two things on a color wheel as far separate as possibly could be the case. And then when it's got these things on the color wheel, it's going to convert them to hexadecimals, and then once it's got these hexadecimals, it can render those two colors. So if we think about scales as being the functions that bring about the aesthetic mapping, then we can think about what these functions are going to look like. And here's a typical scale, a typical function. And it's got a bunch of different components. First, it's got the word scale. Then it's got an underscore. The scales are responsible for bringing about the aesthetic mapping, so there's a word here that typically reflects the aesthetic mapping. Sometimes, but not always, there'll be an additional underscore and an additional word. But of course, being a function, it's always going to have an open and closed parenthesis, although it's not always the case that there's going to be something inside of that open and closed parenthesis. So, another overview slide. We're considering that scales are the functions that bring about the aesthetic mapping. So let's quickly review the aesthetic mappings we've seen so far for the two geomes we've seen so far, geome point and geome line. So for geome point, we map the X and Y locations, the size of the marker, the color and fill of the marker, shape of the marker. And similarly for geome line, the X and Y locations, the size, the colors. Remember that with geome point, with scatter plots, the markers have different shapes. With geome line, a line plot, the lines have different line types. So those are some of the aesthetics we've seen associated with geome point and geome line. And so what I've got down here is a table. And the table is based on the notion that these scales occur in the form of the word scale, underscore, the aesthetic name, underscore, and maybe sometimes another word. Here are just a few of those different scales. So scale Y continuous, that's the one we just saw. And that's the one we use when we map Y onto a continuous variable, the Y location onto a continuous variable. Scale size continuous, we actually saw this one earlier. When we did this thing. Remember, we looked at our plot and we decided the markers were just a touch too small. So what we wanted to do was increase the absolute size of the markers while retaining the relative size. And this is the code here that we saw that could do that. Now let's think about scale X discrete. So here we have scale X continuous. That's the one we saw when the goal was to map continuous variable onto the x-axis. What scale X discrete does, that's the function that's going to be used when we're mapping not a continuous variable, but rather a discrete variable onto the x-axis. Scale color gradient. We earlier saw scale color hue. Scale color hue was the scale that was used when color was mapped onto a discrete variable. But recall, with color, it can be mapped onto either a discrete variable or a continuous variable. So in this particular example, what I've done is I've mapped color on a discrete variable drive, 3 drives, 3 colors. Here color is mapped onto a continuous variable displacement, and so a gradient of colors appears on the plot. So what's shown here is that scale color gradient is the scale that's used when color is mapped onto a continuous variable. And scale shape manual and scale line type manual are very powerful scales that can be used to make user-defined shapes for scatter plots or user-defined line types for line plots. So now what I'm going to do is go through a series of examples. And the first example is going to look at scales for discrete colors. So I'm going to make some sort of a plot 0 here. It's based on a data frame that I'm not going to bother showing. And it's a scatter plot with displacement on the x-axis, city mileage on the highway axis, and color mapped onto fuel with theme black and white. And that's essentially the default that I get. Now I'm going to make plot 1. And plot 1 is going to start off with plot 0, and then it's going to add as a layer, and notice the font is entirely in Courier. You do it exactly like this. And you get plot 1 that has more distinct colors. So those sorts of things would be good if you're doing a PowerPoint presentation or perhaps a poster, but if it's a journal publication and you need black and white, what you might want to do is a plot like this, like plot 2. So that could be produced by starting off with plot 0, adding to it as a layer, and again, note this is all in Courier, scale color gray, so plot 2 is a gray color. And this last one is a really powerful one. This plot 3 has user-defined colors. So I'm going to start off with plot 0, and I'm going to add as a layer scale color manual. Values equals C, red, black. So scale color manual, and there's the open and close parenthesis of scale color manual. And within inside that, I use the R keyword values, then I specify a vector. And I specify a vector with 2 colors stated inside quotation marks. And the order matters. So if we come down here and look at our legend, the different fuels, premium and regular, occur in alphabetical order. And so the order here matches the order here. And so if I specify first red, then premium fuels are going to get red, and secondly black, then the regular fuels are going to get black. And in the same way that we have manual scales for colors, we can also have manual scales for shapes and for line types. So here I've created plot 1, which is a scatter plot with shape mapped onto fuel. And so by default, there's plot 1. That's what I get, and I have these two default shapes, the round dot and the triangular dot. But I could override that. I could create plot 1A. Here's my plot 1A with user-defined shapes. And so I'm going to use scale shape manual. And there's its open and close parenthesis. There's the keyword values. And then I'm going to provide a vector with two numbers that will indicate the shapes that I want to have for those two different fuels. So in this particular case, I've said 8 and 18. And so remember that shapes are numbered. We saw this before. So shapes are numbered. So there's my 8, and there's the 18. And again, order matters. So the 8 is going to go for the first one, and the 18 is going to go for the second one. We can also manually create line types. So here's plot 2, where I've mapped line type onto fuel. And there's plot 2, and by default, those are the two line types that I get. But I can override that by using scale line type manual. There's its open and close parenthesis. And inside that, I say values equal, and then I specify a vector of two numbers. So remember, with line types, there's only 6 different numbers to choose from. I've chosen the number 3 and the number 5, the number 3 and the number 5. So 3, the premium fuel, gets that. 5, the regular fuel, gets that. Scale size continuous. This is the one that we saw earlier. So essentially, we've got a plot like this. We want to increase the absolute size of the markers without changing the relative size. So we just type in scale size continuous, and there's its open and close parenthesis. The keyword range equals, then we specify a vector with two numbers that specifies the minimum and maximum size of those markers that we want. Example 4, changing the axis text. So what I want to do is I want to control the text on the x-axis, so it's 15, 25, 35, 45. Excuse me, that's the y-axis. And similarly on the x-axis, 10, 15, 20, etc. So for the x-axis, I specify scale x continuous. There's its open and its closed parenthesis. Then the keyword is breaks equals, then I specify a number. I specify a vector. And the vector contains the numbers that I want to appear on the x-axis, and they're shown down here. Now, one thing you might want to wonder is, okay, there's a 5 shown here, but there's no 5 shown here. The reason for that is that the data actually begins at a number considerably larger than 5. So the 5 is not going to appear there. On the y-axis, I'm going to use scale y continuous, open and close parenthesis, specify the breaks, specify inside a vector the numbers that I want to appear on the y-axis. Okay, so those first 4 examples were exclusively related to scales. And when I talked initially, I kind of grouped scales and guides together. So talked a little bit about scales. What are guides? Well, the way I look at guides is that they essentially reverse the process of scales, whereas the scales bring about the aesthetic mapping. In a sense, the scales take what's in the data frame and converts it to something in the mind of the computer. What the guides do is take something that's in the mind of the computer and renders it into a form that a human being can understand, and the two main guides are the axes and the legends. So in the mind of the computer, on the y-axis are numbers that go from 0 to 1, and on the x-axis are numbers that go to 0 to 1. And the guides in this particular case would be the axes that tell us, hey, what's on the y-axis is actually city mileage going from here to here, and what's on the x-axis is displacement going from here to here. And similarly, if we think about color, in the mind of the computer, these things here are hexadecimals. And so what they're converted to using the guides is a legend that tells us that, hey, this is the premium and that is the regular. So what I want to do here is going to involve guides in the sense that I'm going to be working with these legends and converting stuff in the mind of the computer to something that is understandable by a human being. And we're going to focus on initially this little legend here. So I've got this little legend here that has a bunch of labels, and I want to change those labels as shown in this legend here. So this is my plot X, and I haven't shown the code to create it, but this plot X exists, and I want to make plot Y. So to make plot Y, I start off with plot X, and then I'm going to add as a layer. Now, if I'm thinking about this particular legend here, where did this legend come from? This legend arose because I mapped the size of the marker on the city mileage. And what's the scale it would have been used to have done that? It would have been scale size continuous. So I'm going to begin with that function. And there's the open and there's the closed parenthesis associated with scale size continuous, which is a scale responsible for making those legends. And then inside of that, I'm going to specify breaks equal and a vector, labels equal and a vector. And breaks equal is simply going to replicate what's currently in place. So if I look at this legend, 10, 15, 20, 25, etc., that's what goes into breaks, what currently is in place. And then, following a comma, I have labels equals and I specify a vector. And inside that vector, I put in the numbers that I want, or the values that I want, 10 mpg to 35 mpg. One thing to note is that there's no quotation marks here. There are quotation marks here. This is a continuous variable. This is now a character because it involves those words. So that's the first legend. Now I want to think about the second legend here that arose as a consequence of mapping both shape and color onto drive. And because both shape and color were mapped onto drive, in order to change these labels, I'm going to have to use both the scale for color and the scale for shape. So, what was the scale that was used when color was mapped onto that discrete variable? It was scale color hue, and there's its open and close parenthesis. So note it's being added as a layer. I'm going to add scale color hue, but as before, I'm going to have breaks equals, and then it's vector, labels equals, and then a vector. So in breaks equals, I put what was initially there for F and R. Notice now these things are in quotes because for F and R are character. Then labels equals, I specify a vector. I specify the values that I actually want to appear. These values here, again in quotes, because they're a vector. This particular legend arose as a consequence of mapping both color and shape. So to change these labels, I'm going to have to use not only scale color hue responsible for the mapping of color, but also scale shape responsible for mapping the shape. And just kind of parenthetically, I would point out that most of the scales have these 3 words. Scale shape is an example of one that only has 2 words. But in any event, the process is going to be the same. I'm going to have scale shape. There's its open and its closed parenthesis. And inside that, the breaks and the labels, a vector for each. First vector is what was previously the case. Second vector is what I really want. And the sixth example is going to address this rather irritating problem that you may have seen. When you look at these markers here, they may be really small in a very irritating way. And we can overcome that problem if we started off with some sort of a plot X that had really small markers here, and we want to increase the size. Here's the code that will do that. And this is clearly a recipe. I have no idea why it does work. I just know that it does work. And so you can see virtually all of this is in Courier. You do it exactly like this. The only thing that changes is this number here that's going to affect the size of the marker. So if we think about the scale, where did it come from? It came from the mapping of shape and color on the drive. Down here, I specified shape. So why did I specify shape as opposed to specifying color? And this example is quite different from the previous example. In the previous example, where I wanted to change the labels, I had to use both scales, both scale shape and scale color hue. In contrast, when I'm trying to play this game, increasing the size, I could use either shape or color. Either of those would be adequate. So, how's this actually going to work? How's it actually going to work when you're preparing your plots for your thesis or for your journal publication? And the first thing you're going to want to do is create your own personal version of my theme. And you'll do that so that you can apply my theme to all your plots, and they'll all have the same general appearance. And there's two components that are going to be present in your own personal version of my theme. First is your overall theme. So you might pick something like theme black and white, although I actually prefer a theme classic. You could pick your personal overall theme, and then you're going to use the theme function. And inside the theme function, you're going to make the minor modifications. So you're going to have your version of my theme in hand. And then to change the titles of the plots and the X and Y axes and the legends, you're going to use the labs function. So the labs function is what's used to change the titles. And then after that, the scales and guides, normally they work in the background, but you may have to use the scales and guides to slightly tweak the appearance of your plot. So now what we have here is a slide that we saw at the beginning of this lab that says, okay, the real purpose is to go from plot 0 to plot final. And how are we going to do that? Well, we went over these basic topics, the titles, the themes, and the scales and guides. So I'm going to assume that some plot exists, some scatter plot that was produced with code like this. And now I want to polish it up for publication in my thesis. So first thing I'm going to want to do is create my own personal version of my theme. So my theme is going to be an object that can be attached to all the plots with a plus sign. And this object my theme is going to consist, first of all, with the overall theme that you really want. Then added to it, there's the keyword theme, there's the open and close parenthesis of theme, and inside of that, you name the element. You name the element, and typically you'll operate on it with an element function. So now you've got your own personal version of my theme in hand. So you get your own personal version of my theme in hand, and what you do is you want to produce your final plot. So you're going to start off with plot 0. You're going to add to it my theme. And you're probably going to want to change the titles for all the plots in your thesis. So to change the titles, you're going to add as a layer the labs function. So there's the open and there's the close parenthesis of your labs function. And inside of that, you're going to specify the titles, and then you're going to give them the values that you want. So I want the x-axis to be the word displacement, and the y-axis to be the word city mileage, and the legend that shows the mapping of size on the city mileage, I want to have that title, and there's my overall plot title. When I've done all that, I can then add with a layer some reference to scales and guides to change those features of the plot that are data dependent. So now what I want to do is just a little bit of wrapping up. And so the first thing I want to do is indicate that some of you may see in your plots and look at those plot titles, and they seem to be scrunched up a little bit too tightly to the plot. So what you want to do is you want to insert some space here and you want to insert some space there. So the general syntax of that is, this is text. And so you're going to use the element text function, and then you're going to specify within the open and close parenthesis of the element text function, the keyword margin, then you have margin equals, and then you're going to have 4 numbers. You're going to have 4 numbers, and they represent the top margin, T, the right margin, L, the bottom margin, B, and the left margin, L. And the reason I point out the TRBL is a good way to think of this is just think of the word trouble. And that'll tell you what those 4 numbers mean. So to accomplish our particular goal, to go from plot 1 to plot 2, we're going to create plot 2 by starting off with plot 1 and then adding as a layer. As always, we're going to be doing these minor manipulations, so we're going to use the theme function, and there's its open, and there's its closed parenthesis. And so as always, we begin by naming the element axis title Y. So there is our axis title Y. It's text. We use the element text function, and then we specify margin equals margin, and then we think of trouble. T, R, B, L. R stands for right, and what that means is that 30 units of space are going to be inserted right of this word city. Now we think about the X title. So we name it axis title X. We act on it with the element function element text. We specify margin equals margin, and then those 4 numbers, T, R, B, L. T stands for top, which means that 30 units of space are going to be set on top of HWY. Copying words to Word or PowerPoint. So up here in my source pane, I've written a bunch of code. I select that code, and hit Control Enter, and there's the plot that I produced. So it may be the case that what I want to do is copy this plot and paste it into a PowerPoint presentation, or maybe make a poster out of it. So how would I do that? Well, it's a little hard to see, but there's a little export tab here. So I'm going to click on that export tab, and I'm going to go copy to clipboard. And I'll copy that plot into my clipboard so it can be pasted. But when I look at this plot, it looks like it's a little bit wide and not tall enough. So up here, I can adjust the width and the height. And I'm going to change the height. I'm going to increase the height. I'm going to change that, let's say, to 1,000. And then I'm going to update the preview. And if I'm satisfied with that appearance, I'm going to come down here and I'm going to copy the plot. So it's going into my clipboard, and then I can paste it into a PowerPoint presentation or a Word document, or maybe make a poster out of it. Something else I could do, which I use far less likely, I could go on this export tab and I could click on Save as Image. And then up here under Directory, I could specify where I want it saved. And then I could give it whatever file name I wanted. Then, as before, if I don't like the fact that it's kind of wide, not very tall, I can adjust this height by making it 1,000. Click on the preview, and now all I got to do is hit save, and it will save it as I want it. So we can copy plots either to Word or to PowerPoint, make a poster out of them, either by using the copy to clipboard or by using the save as image. So, saving for publication with ggSave. If you think about the process that I went through, it will work really well for copying a plot and pasting it into a Word document or a PowerPoint document. The only problem is that if you're preparing something for publication, the journal may require a higher degree of resolution than that previous process is going to give you. So an alternative is to use the ggSave function, and that's what's shown here. It'll enable us to save these plots at a higher resolution. So there's the ggSave function, and there's its open and close parenthesis, and a bunch of arguments that are separated by commas. So the first argument is the name of the plot that you want saved. So that's pretty straightforward. And then you're going to say file equals, that's our keyword, and inside quotation marks, you're going to specify the drive and the folder, and this is the name that you want of the file you want that plot saved as, and at the end, this is the file extension. And this file extension isn't trivial, because in some cases what you want to do is go a certain distance with R, but then the very final adjustments you might want to make in your favorite graphics package. So the whole key here is that you want to save your plot with an extension that'll enable you to operate on it with your favorite graphics package. And I don't know what your favorite graphics package is, but mine is Corel. And with Corel, what I've noticed is I've saved it as one of these guys, having that as the extension, then I can very easily open it up in Corel and make the final adjustments. Specify the height and width of the plot, and I must confess I really don't understand those numbers very well. I tend to operate on a trial and error basis. And then finally at the end, you can determine the degree of resolution so you can increase it to a level that'll be compatible with what your journal wants. So, what we just went over was using ggSave if we wanted to save a single plot. What happens if we've got two plots? We want to combine them into one plot in a way that can then be saved with ggSave. Now, earlier on, we saw grid arrange, and that enabled us to combine two plots into one. And it worked really well for our markdown. It worked really well in terms of displaying this combined plot in the lower right-hand corner. But the problem is it can't be used to create an object that can be saved with ggSave. So what's the way out of the box? The way out of the box is to use a different function. To use a function called arrangeGrob, and that will enable us to create an object that can be saved with ggSave. So down here we've got some code that illustrates that. So I've created an object first called base, and then based on base created these two new plots, A and B. And I want to combine them, but I want to combine them in such a way that they can be saved with ggSave. And so the function I use is arrangeGrob. There's its open, there's its close parenthesis. I list the two files, the two plots, and if I want them side by side, I use endcall. Now having created AB, I can then use ggSave to operate on AB and save it potentially as a high resolution plot. arrangeGrob, down here it's noted, just like grid arrange, in order to gain access to it, you need to install and load the grid extra package. Families and fonts. So the default font for ggplot is going to be Helvetica, but maybe you don't want your text to be Helvetica. Maybe you want it to be Times New Roman or Courier or something like that. So how do you accomplish that goal? Well, first you've got to install and load a bunch of fonts. And here's the code to do that. So if you type this in and let it rip, not only will you install and load those fonts, but you'll also see what those fonts are, and you'll see there's an awful lot of them. Notice this little Y here. So what happens when this thing runs? When it reaches this point here, it's going to prompt you with a question, are you really sure you want to continue? And what the Y does, if you say, yeah, continue, what that means is your computer is going to spend probably the next anywhere between half an hour and maybe as many as 2 hours locked up while it's loading up these fonts. So it's a really time-consuming process. But fortunately, on your home computer, you'll only have to do it once to get it installed, and then afterwards all you got to do is check the appropriate box and those fonts will be available to you. So once you've installed those fonts, then you can use them. So the whole idea is I've got this plot final, and I want to make plot final family, and I want to make some adjustments in the fonts. So not surprisingly, I start off with plot final. I add with a plus sign, there's my word theme. So there's theme, and there's its open, and down here is its close parenthesis. And as always, we begin by identifying the element. So the element is axis title. Now, by virtue of inheritance, axis title is going to control both the Y title, and the X title. And so, having specified those elements, I use the element text function, and there's the keyword family, and I indicate the font that I want. I've also indicated that I want to change the size to 30, but by indicating the family as being show card Gothic, you can see that I've gone from this, which is Helvetica, to this, which is Showcase Gothic. And now I've identified the plot title, its text. I use element text. I've said I want the family to be equal to Bookman Old Style, and I've also changed the color to be equal to orange. So initially, there's my plot title with Helvetica, and now my plot title is Bookman Old Style, and it's orange in color. Down here, again, relates back to this concept of inheritance. And it very likely would be the case that for your thesis or publication, you would want all the text and all of your plots to have the same family. And the way to accomplish that is when you create your own personal version of my theme, you say theme, text, and then you specify the family that you want, and all the text in all your plots will be Bookman Old Style. You can add special symbols. You can add superscripts. You can add subscripts. You can add alphas. You can add omegas. You can add fractions. You can do that in R. It's shown in appendices A6 and A7. But here's the deal. If you've only got one plot in your entire thesis that has a particular symbol like that, instead of going through all the effort that's shown in A6 and A7 and learning how to do that, what you might want to do is save your plot with the appropriate file extension using ggsave, open it up in your favorite graphics package, and do the final manipulations and adjustments there.